basics of computer animation and some 3D geometry problems that are really critical for getting interesting characters that can deform, interact, and move around without like moving around millions of vertices manually. Yeah, so that's our goal for today. Is what do animation tools use behind the scenes? So, of course, if we're going to talk about animation, probably the most reasonable thing to do is to start by talking about traditional animation. And I'm sure that many of you guys have seen images of these artists working, you know, in the old Disney studio. And of course, probably if you went there today, it wouldn't look quite like this. But instead, in front of this lady, she would have a computer. Yeah. But back in the day, what would you do? Well, if you watch these old animated films, you can pretty much guess what happened and how they made it. I know that you guys are millennials and such, but you can probably tell that it's hand-drawn, right? They didn't have a computer to work with. And so, really, these movies, it's kind of an amazing feat, right? That they were able to draw that many frames per second for an entire like hour-long animated feature is pretty amazing, right? And so the field of hand-drawn animation really evolved for these different tricks to essentially minimize or at least reduce the amount of work that it takes to animate something. Right? So for instance, you know, if you watch a Disney movie, obviously the background doesn't change as frequently as the characters that are moving around in the scene. So maybe what you would do is decompose a scene into different layers or cells. Right? So these would be like different sheets of kind of transparent material, and then you draw the background on a separate plate so you can kind of move stuff around and continue taking images rather than drawing every single frame, painting it independently. Yeah? So that was the basic technique of cell animation. It's really quite simple, right? It's all about decomposing a scene into the individual pieces that are going to move around and interact, and really drawing every single frame, which, as you can imagine, is not a super pleasant job. So anyway, typically what you'd have are like the really you know, the high-level upper executive animator types would draw the keyframes, right? So these would be like sampled maybe every second or two to kind of communicate the broad strokes of the motion that you're going to see. And then if you have, you know, the less well-paying job in the animation studio, you could be an in-betweener. Right? And what that would mean is you take all the individual keyframes, which are sampled, you know, spaced farther apart than you would like your frames in your actual video to be, and then draw the pose of the character in every single frame in between. You know, this is a tough job, especially one to do in a way that gets both expressive and, you know, not annoying and jerky motion. Yeah. And then cell animation really evolved to have all kinds of cool tricks, right? So for instance, as a geometry person, one thing that I really love is looking at these images where they've taken the panorama of the whole scene. Where like you watch these Disney movies, sometimes the camera kind of scrolls, and in reality what happened was that they you know, painted the scene on a longer sheet that is your video frame, and then they just kind of moved their image across that sheet. And one thing they would do, this is called multi-perspective panorama, is slowly kind of morph from one perspective to another along the sheet. The idea being that as the camera moves, you want to simulate camera motion through the scene, even though all you can do is scroll this thing horizontally. Right? So these people were actually solving some pretty advanced, tricky geometry problems to kind of warp the 3D world onto a flat plate in such a way that they could scroll across. Another cool idea that they have is this idea of multi-plane cameras. And in fact, I thought what better way to introduce it than to hear from Walt Disney himself here. So,
now, this is a different kind of drawing. It also came out of our school of self-improvement here at the studio. It is the blueprint of a piece of equipment designed to make cartoons more realistic and enjoyable. This is the plan for a super cartoon camera. We call it the multiplane camera. It was intended for use in our feature-length cartoons. You see, we decided for features. The camera needed improvement too. Actually, the pre-feature cartoon camera was fairly simple in construction and operation, and generally very satisfactory. The problem was how to take a painting and make it behave like a real piece of scenery under the camera. The trouble was we were photographing a flat two-dimensional background. So we set about making plans and blueprints for a new cartoon camera that would overcome this. The different elements in the scene were separated according to their varying distances from the viewer. This put the moon on a plane farthest away from the camera. With our original picture broken down in this manner, it is possible to control the relative speed with which each individual part of it moves to or away from the camera. But the moon remains absolutely still. will always remain the same, neither growing nor shrinking in size. Since this new camera used many planes, we called it a multiplane camera.
Okay, so anyway, you guys can see some of the really cool magic tricks that these guys are using, right? So the multiplane camera would be like, I have a camera that's zooming, and so the perspective is changing, and they literally just simulate it in this small version that they're capturing frame by frame at the Disney studio. And I wouldn't want to be the guy that accidentally bumps into the multiplane camera and loses all the alignments, right? So eventually, historically, of course, this is a very painstakingly difficult process. And so what happened is that Disney replaced that entire pipeline with something computer-aided, and this is called CAPS. And this is really a milestone in the history of computer graphics. It's sort of the first computerized animation system, but the really amazing thing is it really did show up in a lot of the movies that we probably kind of know and love, right? All this golden era Disney animation films, whether it's The Little Mermaid, Beauty and the Beast, Aladdin, all this stuff, were actually made with computer software, even those that date back to the 80s. Which I know is the Middle Ages. So here's one of the earliest films. Sorry, these videos are a little dated.
Here at Disney Studios, some interesting experimentation is taking place with computer animation. After setting the trend with Tron, animators turned their efforts to a test based on a classic book by author Maurice Sendak called Where the Wild Things Are. The object was to make the backgrounds with a computer and incorporate classic, hand-drawn Disney character animation with those backgrounds. In this way, squash and stretch, the elements of elasticity that make Disney character animation stand out from all the rest, wouldn't be lost.
What they can't do these days.
In hand-drawn animation, the next step after the storyboard has been completed is the pencil test, a rough pencil drawing to show the action. In computer animation, that step still occurs. It's called the vector test. This is the vector test for Where the Wild Things Are, which Magi Synthavision did for Disney Studios. Once the vector test is approved, the real work begins. Each piece of vector animation must be modeled and shaped. In this case, the characters were painted by computer. The whole process is like stretching a layer of skin over a wire mesh frame. Now, let's take a look at the test for Maurice Sendak's Where the Wild Things Are, which was directed by John Lasseter.
Reproduce this screen test from the 80s. And by the way, in case you're thinking this is dated, really the same pipeline exists today. So for instance, when I was working at Pixar, typically what they do is they'll have the artist kind of block out a scene and really have these kind of funny polygonal objects that are doing the acting in a very proxy sort of low frequency way, and then they'll fill in the animation just like what you saw here. And so it really, the more things change, the more they stay the same. That a lot of the technology and the techniques that we see today date back to CAPS and really are what gets used in practice. So I encourage you guys to take a look at this historical paper here by John Lasseter, who's still at Pixar as far as I know, on computer animation, where essentially what he argues is that the same basic idea of in-betweening and choosing keyframes makes a lot of sense in the computer graphics context. Right? And as you guys can imagine, it also sounds an awful lot like splines, which we've already talked about in this class. Right? You choose a few knots, and then the spline is serving the purpose of being your in-betweener. Right? Rather than drawing a lot of frames, the spline is making a nice smooth path that connects all this stuff. If you like these kind of ideas, I encourage you to take a look. There's a really beautiful book called The Illusion of Life, which talks a lot about the different techniques that they use in these animated systems. And one of the reasons, and in fact a lot of my PhD students will spend time looking at this kind of material, because at the end of the day, our job as graphics engineers, especially when we're working in this sector of industry, is essentially to capture the type of expressiveness and motion and things that they're trying to get. Right? That when you design animation software, your goal is to make the animation software communicative and capture all of the motions and rendering that you would expect in just a hand-drawn tool, right? So returning to these basic, kind of classic books and seeing what they recommend is a great way to help you understand how to design your user interface, know what kind of features to include, and so on. Yeah. So one of the really basic examples that most of us know about is squash and stretch. So one thing you might not have thought about explicitly is when you look at animated cartoons, they often have, it's fascinating, they have their own physics, which is not F equals MA, but is self-consistent. Right? And so one of the great examples in Disney animation is this idea of squash and stretch. So for instance, if you have a bouncing ball, you see maybe the path of the bouncing ball on the slide here. What do you notice? Well, for one thing, the ball knows that it's going to hit the ground before it touches the ground because it kind of stretches, in that direction. And then similarly, it kind of anticipates its motion, right? There's this exaggerated thing that goes on here, right? And so one of the earliest efforts, and indeed when you use splines, they have exactly the same property, right? When you're controlling tangents and widths and so on, was really all designed to capture these notions of squash and stretch, which exaggerate motion in sort of an expressive way. A related issue to that, of course, is timing, right? That maybe light objects move more quickly, heavy objects move slowly. If you're Newton, you might disagree with that. Right? We know that all things have the same acceleration due to gravity, but not of the correction. And that's one of the really neat things here, is understanding essentially the version of dynamics that happens in the animated world, which, by the way, can change depending on what film you're making, right? Ratatouille might not be subject to the same dynamics that Cinderella was, which is a really interesting thing to think about if you start to philosophize a little bit. Right. So, of course, we've evolved quite a bit from these cute hand-drawn things to fully rendered 3D models with environments and shading and so on. One of the nice things about films, of course, is that it doesn't care how much CPU time it takes to generate a nice looking frame. Right? And so, for instance, I think some of the frames in Pixar's Cars movie took up to 100 hours to render. Right? Remember that a movie is 29.97 frames per second. A lot of computer time goes into this. And in fact, a lot of the evolution of parallel computing and so on dates back to the computer graphics world. Of course, on the opposite extreme, sometimes in computer games, you have to render a frame inside of your laptop at exactly that rate, and then your job becomes quite different. Right? It's not to get the best quality expressive motion, but rather to figure out how much you can fit in the CPU time you have available. All right, so with that little kind of broad overview of the types of issues that we see in animation, now our job is to fill in the details. Right? And so we're going to talk about it both from a kind of mathematical point of view, as well as sort of how we go about designing controls in a way that's useful. So as I already mentioned, the main type of animation that people think about is keyframing, right? Where essentially you have, for example, I don't know why you would have a rigid bunny floating through space, but if you did, then maybe you specify its position and the tangent of its motion at sort of sparsely sampled points in time, and then you use tools like splines to animate in between them. By the way, kind of a subtle thing that's inside of this figure that probably we don't think about is coming up with splines in rotation space, which is actually an open problem computer graphics people think about still. So it's amazing that even really simple things like transitioning between different rotations of an object is pretty tricky. It actually appears in robotics world as well. But this isn't the only type of animation. So for instance, another type of animation is called procedural, and the idea here is that I don't just specify a bunch of frames, but rather I write a piece of code that gives rules for generating my codes, right? So a really simple example here would be maybe I have a really crazy, well, not a crazy watch, a completely standard watch with, second, minute, and hour hands. Hopefully you guys have seen a watch that looks like this. It's not just digital now. And, right, so an example of a procedural animation might be that I tick the time forward, and then behind the scenes, my code works out the positions of the different hands of the clock, rather than explicitly giving key points for all of those positions. Hopefully you guys see the difference there. A third type of animation that's quite popular in films now is physically based animation. The idea that different objects have physical properties, and that essentially the motion, the interesting motion that you get in a scene comes from simulation of physics. And notice, of course, that one thing we can do in this world that we can't do in the aeroastro department is change physics. Right? So if we want a different type of motion, we can get it. And what we'll see, and we'll see this in the next couple lectures, is that physically based animation is obviously more realistic. You can capture things in the real world, but it's very difficult to control. Right? So for instance, if I wanted a movie, I'm a kid and I drop my pile of toys, and I wanted to spell out my name when it drops on the floor, it still look like I dropped stuff. I mean, if you think about it, that's a really hard problem to solve in real life, right? Like, where do I place it in my hand so that when I drop it, it goes exactly the right way? And effectively, computer graphics people are asked to solve that all the time. Right? And so there are two different things you can do. You can either solve a very large-scale, non-convex, God knows what optimization problem to try and actually work out like the initial pose of my hand that would make that happen. Or maybe I combine these different methods of animation, right? I add keyframes, and then I say, in between the keyframes, I'd like my motion to be as physical as possible while obeying what I really wanted to happen. Yeah? And these are the types of things computer graphics people have to deal with. Of course, in pure physically based animation, I had to update the slides from this course because every year they change quite a bit. Here's some examples of fluid simulation. Judging from these images, this looks like a particle-based fluid, but I could be wrong. And this is all rendered. This is purely virtual. And it comes from tunes. So you can see the technology for fluid simulation, which is physically based animation, right? This is made digitally. It's extremely advanced. Yeah.
So it does like physics simulation.
Yes.
But in order for us to see the liquid, because it's not obviously like completely transparent, it's doing like ray tracing.
Yeah. So so we're going to talk about the motion first. The other aspect, as of course, you can see, for example, in this scene here, is rendering, right? How do you actually draw fluid? And so in your next assignment, you're going to be simulating cloth, and you can use some very simple rendering. And then later on in this course, when you start doing glass and things that are transparent and reflective and so on, we'll learn about that as well, for sure. Yeah, but it's absolutely a good point. That it's not enough to just have a nice simulation. You also have to draw it this way. Yeah. Okay. Another context where physically based, and by the way, you guys should watch this movie. It's really fun. And another great a place where you can see physically based motion is actually character animation. Right? So let's say that I want to simulate somebody, jumping over a box or lifting weight or whatever. There's all these little wiggles and things that happen that you probably wouldn't want to keyframe, right? And so techniques like this essentially are designed to fill in your keyframes without all that work.
The laws of physics, strength limits, and joint limits all place natural bounds on a set of motions, and this results in a subspace of realizable motions. Optimizing a motion for minimal effort or other criteria has commonly been proposed as a way to help select the single best motion from each space. We propose an alternative solution, one that can produce highly diverse motions that help the user understand the range of possibilities. Given an input motion, a set of maximally diverse solutions are synthesized as measured by pairwise distances between all the motion variations. On the left, we illustrate the diverse range of motions that can be achieved for our jump example.
So as you can imagine, it would be very difficult to keyframe all of those different kind of secondary things that happen that this guy jumps over stuff. And so they use physics to fill in that detail. Of course, one of the neat perceptual effects, I think, is a lot of people in the room are probably just impressed that this guy can do a backflip. Of course, he's just a virtual camera. Yeah. Right. So there's some really impressive results, and this really does get used in practice, as you can see. This is called space-time optimization. The idea that I have keyframes with my motion, so I can't just simulate it forward in time, because I kind of have to hit, he has to stick the landing. But I'd like it to still look physical in between. Yes?
What are like the different variables being tweaked to make them look different?
Sure. So there's the joint angles as a function of time. There's his position. I think in this case, how much he anticipates the motion. Like, does he kind of get ready and then jump, or does he just go right into it? Yeah.
That's fine. But this is anticipation. Is it getting momentum, or is it just like trying to?
Well, one of the really interesting things is that it turns out that a lot of what we might view as sort of intelligent design, like kind of getting ready to jump, is sort of necessary to accomplish certain physical motions. And so some of these optimization problems, and some of the modern tools are actually able to capture that without very much guidance. It's a really fun area of research. You guys should look at, just go on YouTube and watch some of these videos. They're really pretty cool.
So is the motion generated by the virtual muscles of the?
I don't know in this particular paper what they're doing. I think they have some keyframes and they're just trying to fill it. Yeah. Okay, there you go. You watch this all day. Okay, so those are the basic types of animation, right? We have keyframing, we have where you just specify motion and like nothing too exciting happens in between, it's just something smooth. There's a procedural animation where I write a piece of code that generates an interesting motion, and basically this. And of course, I'm sure you guys will come up with many more techniques, but these are three basic ones. So now we have to talk a little bit about animation control. So remember that, you know, at the end of the day, when we render these models, they're probably going to be triangulated surfaces that are composed of like tens of thousands of little triangles. And what would not be feasible would be like, so I have to give, you know, the path of every single vertex of this 10,000 vertex mesh as a function of time, right? So instead, essentially, the world of animation is all about how do you give the right set of controls to your problem that are sort of high-level, you know, numbers that control your motion and can be translated into the vertex position. So that's essentially today's lecture topic. And you also heard about it in the last one from Bo as well, right? So an example would be maybe the angle of a joint, you know, whether you're standing up or down, or simply a transformation as a function of time, right? So if you have this flying rigid bunny, then it's enough to just know where he is at any given point of time to animate. Yeah. So there's a nice example of controls. I couldn't get this to work on my laptop, but you guys can try it at home, where essentially Ken Perlin sort of looked at you can see it very clearly, right? This is a triangulated surface. And then rather than specifying the locations of all the vertices, he managed to come up with sort of linear combinations of vertices that, for example, if you smile, obviously everything in your mouth kind of moves in a similar direction. So there's this fun little app that you can kind of slide these things around with this person in different poses. And so typically what people do is they try to come up with like semantically meaningful controls for their animated character rather than just like really low level numbers of where's this point. Yeah? And so coming up with those is the trick. And this is part of, this is part of the animation pipeline, which is very typical, where you start with the story, and then the very next thing you have to do is make what people call the assets for your movie. These would be like the 3D models that you have. And the next thing you have to do is figure out how your assets move, right? So for instance, you've probably seen images of like, you know, like characters in The Incredibles or whatever, and they always are like standing like that, right? So that would be the basic 3D model in what we call a rest pose. It's never actually a rest pose. And then the next thing they have to do is say, well, what happens if I actually wanted his arm down, right? And so that second part is called rigging, right? It's giving controls that tell how the mesh moves as a function of different parameters, like joint angles. Okay, that's called rigging. We're going to talk about how to do that. So you already heard in Bo's lecture, of course, that there's sort of two things involved in rigging, right? One of them is forward kinematics. This would be like, if I give you the joint angles, then you give me the 3D mesh. Right? And then inverse kinematics, which is going to be important, and I think we'll talk about it a little bit later on in this class, will be like, well, at the end of the day, like let's say that I had a protractor and I could just measure like the angle of every joint that you have. And I said, okay, give me the joint angles so that you reach over and grab this sheet of paper. Right? That's a really hard problem, right? Because like for instance, this arm at this angle will be different depending on like the angle that's above it. Right? So it would be very difficult to like accomplish a goal. And so the idea of inverse kinematics would be like, well, at the end of the day, I'd like my hand to be here, and so I'd like to solve for the joint angles that accomplish that. You guys see the difference? So forward kinematics is given joint angles, just pose a 3D object. Inverse kinematics would be like, figure out the joint angles that give me the pose I want. Yeah? Okay. Right. So then beyond the basic kinematic model, I mean, obviously these like 3D dudes built out of blobs are not what we want to render at the end of the day, right? We want a nice skinned 3D model that actually looks like, you know, a human being with skin stretched over them. Yeah? And so that's our next goal, is to do something called skinning, right? And the idea, I see, is that given the basic pose of like some rigid skeleton that's sitting underneath your model, how do you actually get the nice 3D bench geometry of the shape you're going to render? Yes? Question?
I'm just wondering, are neural nets used nowadays? Do they do a good job of solving problems?
Are neural nets used for this stuff? Yeah, so there's some, we'll talk toward the end of lecture today about some challenges involving like skinning, like actually coming with skinning weights and so on. My impression is that for the most part, these are done with just convex optimization tools. but there are some neural net things involved to kind of capture semantics. But this would be a very new idea. Yeah. In general, neural nets applied to 3D data is an open research problem. In fact, one that my students and postdocs work on. So I'm happy to tell you a lot about that afterwards. Yeah. But for now, we're going to do the non-neural net version of this. Okay. So, so the idea, again, of skinning is that I'm going to animate the bones, the joint angles, and so forth, and then what's really going to move is this 3D model as a function. And so what we have to do is a process called binding, which tells you how the vertices of the 3D mesh, right, like these 10,000 things that I'll have to move when I animate a character, move as functions of the skeleton. This is binding or skinning. Of course, this is going to come up a lot in today's lecture. I'm going to tell you the basic word, and then I'm going to give you like 10 other options of different ways to accomplish the same task. So another way to go about this, rather than doing forward inverse kinematics, that's very popular in some movie studios, is called motion capture. The idea here would be maybe I attach a bunch of markers, like you wear a little suit, and now I'm an actual actor that acts out a scene, but I'm controlling a 3D character by tracking where those markers move and then mapping those onto the motion of the 3D character. Mocap technology changes all the time, and one of the cool things to see, like literally just in the last 5 years, is to see how it's evolved, right? So, for instance, at the kind of high end, maybe you actually add markers. So you can see here, this actor, has obviously a bunch of stuff on their face, and then why do you do that? Well, that makes it very easy to focus points in the camera frame, and then your computerized system, marks the same points on the animated character. Yeah. Now, obviously, if you're Brad Pitt and Angelina Jolie and you show up at the computer graphics studio and control Shrek or whatever it is that they animate, it would be a very expensive proposition to get some snotty actor to attach a bunch of color balls to their face. Right? And so one of the big pushes in the motion capture world has been to do what we call markerless motion capture, where you just capture video of somebody acting and you solve this really tricky problem of like how to control a 3D character where your input is just like video feed. Right? This is very different from like there's a giant purple point on her face that's really easy to find. Yeah? Okay. So right. So in other words, so motion capture is capturing all of these 3D marker positions. Of course, then you might have to solve an IK problem, an inverse kinematics problem, to actually go from those marker positions to, again, the bone positions from the face. Right? So you can't get away from this stuff, no matter what. Okay. Now, more modern pipelines are for markerless motion capture. So this happens to be my friend Sofiane, who now works at Apple. And you can see this is the feed that comes in, I think, from the Microsoft Kinect test a few years ago. And their job is to get essentially what you saw with markers, but with far, far less information. Yeah, like that. And so they do remarkably well reconstructing this stuff and moving along. By the way, if you're ever trying to evaluate these systems, always look at the mouth and the eyes, which tend to like vibrate a little bit because they're very hard to track. This paper is a complete as well. Okay. So in fact, it was just in the news recently. Did you guys see markerless motion capture in the news? Let's see if I can even play. Right, so if you get the next iPhone, you will have markerless motion capture so that you can send custom emojis. Right, so I believe the author of this paper I just showed you, this is where he's now working.
Given access to the most advanced facial tracking technology available, you now have your answer.
So if you're looking for practical applications of
these could be so much fun. You're
you can see them in your next iPhone. Will actually be a little motion capture device that you can hold in your hand. It's really amazing. And you can animate the poop emoji. All right, guys. Of course, on the high end, another reason why you might want motion capture, markerless motion capture beyond just like actors being annoying, is that sometimes you're interacting in a very complicated scene, right? And in that case, it might be really difficult to have the actor like wear all kinds of stuff on their face while they're like trying to lean into whatever this is, like an organ or something, simply because the way having stuff attached to your face, it affects the way that you act, right? And so, like for instance here, this is the input to the Disney system. He does have, it looks like, small markers on his face, but far less information. And this is, I think, Pirates of the Caribbean. Of course, this is Davy Jones. You might not know it from this, but you probably do know it. And so you can see that all of the things that we're talking about today looks like the lighting changed, like as well. That's really are used in the movie pipelines. Yeah. Right. So as you can imagine, forward kinematics is an easy problem. That's what we'll mostly talk about today. Inverse kinematics is much trickier. That's very nonlinear. Okay. So for the rest of our day today, we'll be talking about character animation. Right. This is different from like, you know, animating droplets of water. We're specifically going to talk about, you know, animals and humans and things, and the techniques that we use to animate those in the graphics pipeline. And as we've already mentioned, this is really all about skinning or enveloping, depending on who you talk to. Right? And it's really key to do this efficiently. Right? Even more so in the, you know, the 3D video game world, where your skinning has to happen 30 frames a second, in parallel with all the other stuff that has to happen to make a video game work. Yeah? This is tricky stuff. Okay. So we already know, hopefully from our last lecture, unfortunately I wasn't there, we already know how to animate a bunch of bones, right? Because we talked about transformations, right? So we talked about how to, like, for example, if I know the joint angles and I know how the joints are stacked on top of each other, right? Then, like, how would I get positions on your hand? I just multiply a bunch of matrices, right? That's the pipeline we talked about. So at the end of the day, we know how to, like, get positions of bones given joints, right? And for instance, if you want to animate, what would you do? Well, you could take a spline in joint angle space as a function of time, right? So this would be like a smooth, you know, set of joint angles that changes as t moves forward. And what you get is a nice motion of your character. By the way, it's easier to neglect that, but it's actually ridiculously cool that you can do that, right? You're taking like splines in like 0 to 2 kind of space, and you're getting a whole motion of a 3D character that's reacting to that. So obviously, there's a little bit of stuff that's going on. So what we're going to do next is we're going to embed a skeleton, which is the thing that we know how to control so far, in the interior, roughly. It doesn't turn out, it doesn't really matter. Obviously, you're not going to render the skeleton. Into the interior of a 3D model, and bind the skin vertices to the bone vertices, right? So in other words, as I animate the skeleton, the skin will move as a function of the positions of the bones. Yeah? Okay. So that's this process called skinning, which I think at this point you guys got to get the idea. And so today we're going to cover what's probably the simplest and best known technique, which is called skeleton subspace deformation, SSD, or people just call it skinning. Like if they don't attach like something fancy like dual quaternion skinning, then they probably mean just skinning. You guys get it, that's actually a thing. Yeah, it comes under many names: vertex blending, matrix palette skinning, linear blend skinning. These are all models. Okay. So, what do we have so far? Well, we know that so what we're going to do in SSD here is not solid state derived. Again, this is skeletal subspace deformation. I have no idea which one came first historically. Might be this actually. Is that every bone is going to imply a deformation of the space around it. Yeah? And so far, all we know is a deformation of a bunch of like little line segments. And essentially what we're going to do is we're going to say for every point in kind of all the space around your bones, we're just going to give some kind of deterministic function that tells you where those points might be. Yeah, that's our job to decide. And so the first thing you might do is you might say, well, we do know how to move bones. What if we just say that every vertex, every vertex on your skin is attached to its closest bone, and I move it just as a function of the position of that one bone? Yeah, would be a reasonable starting point. What do you think would happen?
Like you wouldn't get folding skin, things would just like phase into each other.
Exactly. I mean, it would look like a bunch of rigidly moving objects. Right? It would be like you took your whole body and you made it out of sticks of wood, and now you're trying to animate that. Right. In other words, your skin would be rigid, except at the joints, where, like, what's going to happen? Well, if you have an elbow, you're going to have one vertex in your elbow attached to this bone, another vertex in your elbow attached to that bone, and effectively, when you bend your arm, you're just going to get like a giant hole in your elbow. That's not so good. No? Some experience. It's not so good. Okay. So, right. So instead, the way that we're going to get around that in SSD is we're going to attach the vertices of the skin mesh to more than one bone at a time. In particular, if you have a vertex right close to a joint, then you're going to say that the vertex moves as a function of both of the bones that are adjacent to that joint. Does that make sense? No. Okay. What can I clarify?
Like, is it still a single vertex or you have
Well, that's a good question. So in a sense, if I did move a vertex rigidly as just attached to one bone, you would all of a sudden have two, right? And then one thing I could do would be average their position. You know? That's roughly what SSD is, right? Right. And this is going to give us some simulation of folding. In the newer computer graphics pipeline, this has been replaced by more complicated models that actually try to capture the elasticity of your skin. But as you can imagine, those are very expensive computational. Right. So roughly, here's an example where here's a hand, and then what they've done is they've segmented the hand, and they're saying that, for example, these points at the back of the hand, if I just have one bone that's controlling this kind of position here, really do move more or less visually with the back of your hand. And then what they're going to do is in these black areas, they're going to say these are sort of transitional areas where the positions of these vertices depend on the position of one bone. And so notice that these tend to be near joints, obviously, right? Because that's the places where stuff stretches out. Yep. Here's another example for a human. You can see these are pretty noisy, so these were not designed by artists, these were designed by some automatic scanning system. Right? So it wouldn't be good enough for cars, or whatever the latest things are. Okay. Right, so to start with, what we're going to do is we're going to say, remember that a bone is a bunch of joints. They're connected by range of motions. We're going to say for every bone, we're going to give it what we call a weighting function, right? So for every vertex pi, you know, or for every vertex pi of the outer mesh, and for every bone vj, I'm going to have a weight wij, which is equal to the influence of bone j on vertex I. And we'll assume that these guys sum up to 1 over all j. In other words, sort of the total influence on any single vertex of the mesh of all the bones on the entire skeleton sums up to 1. Yeah, so hopefully that makes sense. And you might ask, like, well, how do you get these weights? Well, typically artists actually will draw them, right? So this is part of this rigging process. You'll embed the skeleton in the interior of your mesh, and then an artist will actually paint on the skinning weights that are attached to the different bones. Yeah. As you can imagine, it's like not a pleasant process, so a lot of work has been done in like the SIGGRAPH community to try and come up with automated computer systems for it. And there's some pretty advanced ones at this point, but still artists don't use it. They prefer to draw them. Right, so typically you want these things to sum up to 1. You also probably want it to be non-negative, right? So for instance, it would be like if I bent my arm and all of a sudden my elbow went out, right? Because I had some negative weight in the motion. That would probably not be a very desirable thing unless you kind of understood ahead of time that that's what you really wanted. So typically they're not only sum to 1, meaning that your total influence is 100%, but also you don't have negative influence. In other words, if something goes to the left, that it would move to the right. Yeah. Okay. So right. And typically, you limit the number of bones that can influence a single vertex. Right, so typically it's 4, although there's no real thing here. But there's sort of 2 big reasons why. One is just like, how often do you have a skeleton that like 7 different bones in your skeleton are all controlling at some point of your surface would be a pretty crazy object, except maybe an octopus. But also, remember that with every sort of influence you add, you are going to have more computational time, right? So we're going to talk about an algorithm in a moment that essentially determines your position as a function of the bones nearby. And with every bone that you add, that's one additional little set of arithmetic that you have to do to calculate your location. Okay. So at the end of the day, we're given some pose of our skeleton. We're given these binding weights, right? These wij's, which tell you how the bones affect the positions of the different points. And what is your job? It's how do you compute the positions of the mesh in terms of the positions of the bones. Yeah, that's what we're going to do. Okay. And so there's a really kind of sneaky trick that they use in SSD to get what is, I would consider, a plausible deformation of skin. Now, again, this is going to come up a lot. Like when we talk about, I think our next lecture is on physically based animation, like simulating cloth and fluids and so on. This is physically based animation, right? And similarly, this is physically inspired skinning, right? So there's no elasticity going on here. There's no, muscles and bending, stretching, and fibers and so on. There's just something that somebody has decided looks kind of like bending skin, and it's easy to do computation. Right? I want to call that out right now because this is not like some God-given algorithm. This is a heuristic that works well. Okay. So the idea here is what we'll do is, first of all, right, every bone has its own coordinate system, yeah? And I could model the whole 3D mesh in terms of any single bone. right? Like and essentially I could transform every vertex as if it were just attached to one bone. Yeah? But I could do this for every pair of vertex and bone. Right? In other words, like if I move my leg, I could move my vertices proportional to that motion. Right? I can do that for every pair. And then what do you think SSD does is it just, all it does is it says, okay, well for every bone position I have a slightly different pose to mesh, which is just moving rigidly with that bone. And now I'm just going to average those. Yeah, so that's the idea of SSD. So in other words, right, so if Pij prime is the position of vertex I transformed using bone j, in other words, like I move up my leg and I move my arm the same way, right? Then what I'm going to do is say, okay, I'm going to sum up these Pij primes with the weights W, right? And so these are what's going to give me the plausible motion. In other words, this is saying that a point here should be mostly influenced by this bone, whereas a point here should be mostly influenced by that. Cool? Okay. Right, so let's take a look at this in a little more detail. So, right, so let's say I have two bones, and these in two different transformations of space. In other words, I bent my arm, right? So this bone wants to rotate 90 degrees and move up, whereas this bone didn't move. Yeah. So now every vertex has two options, right? It can either rotate 90 degrees and up, or it can not move at all. Yeah. And now I'm going to combine those two different options with the different weights attached to the bones. Yeah. And so what you'll get at the end of the day is that assuming that the skin right close to P0 has weights that look like 1/2, 1/2, and here the weights look like 1, 0, and here the weights look like 0, 1. Right? When the weights are 1, 0, what do? Well, I rotate with this bone. When the weights look like 0, 1, I rotate with that one. And when the weights are like 1/2, 1/2, I average those two results. Yeah. Okay. And so that's what happens here. Right? So as I bend this elbow, this skin kind of stretches out in between because you're trying to compromise between these two different rigid motions that you see on the side. And when I say compromise, I really mean just average. So one thing to note, like I already told you guys, this is certainly not physical, and it's very easy to come up with counterexamples. In particular, notice that I drew you the nice side of this guy's arm, which is what happens when he bends his elbow. But what do you think happens in the, what do you call this, the armpit of the elbow? I don't know. Yeah?
Does it just lift with itself?
Yeah. So this is, so take a look, right? So if I trace a vertex right close to this vertical line, like at this point on the rectangle, what happens? Well, this transformation says it should go in. This transformation says it should go the other way. So in reality, I could even get like a loop in the arm. You see that? And indeed, that's what happens. So this example is not quite as extreme, but you can see that you get this kind of funny dip because I haven't done anything that knows about the meat inside of your arm. Right? I'm just averaging a bunch of positions. Yes, Efrain? Yeah.
Also, your skeleton, how you find math, you broke the rules and run it. So you already have it.
It broke the rules. Who
You
made
already
the
know
rules?
it's like non-physical, right?
Yeah.
So how the skin does it, it's not. I mean, if the bone wouldn't be allowed to touch it, the bone itself is actually.
Yeah, if the bone, we're not allowed to go into. Well, the way that we've drawn it here is already kind of funny because your bones are not like rectangles that just are smashed up against each other. This is just a representative picture. But you're right, you could try to add constraints that say that your arm just shouldn't bend at some point. That would at least prevent some of the extreme cases. But this is still not physical. There's nothing about this. This is actually what your skin would do. Yeah, that's the larger issue. And so, indeed, this happens, right? If you watch some of the older 3D animated movies and video games, you'll see that when the characters move, there tend to be these kind of funny changes in geometry that don't look particularly physical near the joints. And the reason is that they're using this technique, and so that's okay. Right. So that's the basic technique. It's really simple. It's one of these things that's like notationally kind of annoying to think about, but at the end of the day, it's more or less probably what you would engineer at home, right? Like I have some number that tells me the influence of different bones on a vertex position. What do? I move things with those different bones, and then I just average the rest. Yeah, that's the system. Okay. So now let's talk about a few details of SSD. One of them is that we need to deal with something called the bind pose. Right. So the idea is that I have to figure out how everything moves as a function of the skeleton. Right. So I need some communication between the skeleton and the 3D mesh. That's beyond just those influence weights. Right? Because I also have to figure out what happens in rigid motions of space, and obviously different points, like if I pivot about this point, right, that's different from pivoting about this point, so I need to know something about space, not just weights, like in terms of the influence of my bone. Yeah? And so this is called a bind pose. So the idea is that when I make my basic 3D model, we agree ahead of time to like put the model in some basic pose where I can easily embed a skeleton. To take probably the skeleton where all the parameters of the skeleton are 0 and kind of build the mesh around it. And now, what we're going to do is to use this as a clue for how to move stuff. You know? So in particular, the only 3D mesh that you have as input to your innovation system is the bind post of the skeleton. Right? Everything your software is going to generate is how the stuff should move as a function of the bind post of your fingers. Okay? So really, these undeformed vertices pi are given in just some coordinate system relative to this full rigid do. You know? And our job is to modify that. Okay. Right. So in other words, we kind of conveniently forgot that in order for this relationship to make sense, we need coordinate systems to match up for each of these pieces: tj, pi, pij. So that's going to be our next chapter. Which you guys have already seen in this class. It's the kind of calculation you tend to screw up. So hopefully we got it okay. Okay. So we have undeformed vertices pi, which are the object space of the skin. When I say object space, what I mean is that literally we're given a triangle mesh. There's just like a list of positions for all the vertices of the triangle mesh, and that thing has its own little coordinate system. Those are your undeformed positions. Now, tj is in the local bone coordinate system. In other words, the bone maybe rotates about some joint, and then tj is expressing that rotation. Yeah? So what do you think I have to do to put all these things together? I kind of have to map from the coordinate system of this 3D guy to the coordinate system of every bone. Yeah? And that's what we're going to do. So in the rigging phase, we just line these things up, and this gives some rest pose with what we call bone transformations from the local bone coordinates to the global ones. In other words, remember that in the rest pose like this, yeah, the bone, like your bone of your finger has its own little coordinate system where like maybe this is the origin. Yeah. So this transformation B is going to go, I always get it from and to confused here. I think B goes from local bone coordinates, like where this is the origin, to the coordinates of this guy in the bind post. Yeah? Okay. So B, it's very easy to obtain B, right? So what do? Remember that we have this big hierarchy of transformations? Right? So to obtain this Bj, I have this guy in his rest pose, and I just compose up the hierarchy that you learned about in the last lecture to get to the global coordinate system, which is where this triangle mesh goes. Okay? And that's what this B is. It's the product of all those matrices. Okay. So again, it goes from the coordinates of the thing at the bone all the way to the coordinates of the mesh that it's in. Cool. For the bind pose. Okay. So now we animate the model. The bone transformations change, right? The bone is no longer in this position; it's in some other one, right? And so what do I have to do to deal with that? Is I need the bone transformation tj, right? By the way, tj and bj would align in the rest pose. Yeah. Okay. So right. So now I have a new set of coordinates, and these map from the local coordinate system of the bone to the world space of the deformed character. Yeah. And these also concatenate a bunch of matrices, right? They concatenate the ones to the dented guy instead of the guy in the one below. Okay, so, right, so what do we need to do to deform pi? Well, the first thing I have to do is take my point P and write it not in the coordinates of like my feet, but in the coordinates of my finger. Then I have to apply the motion of my finger, and then I have to undo all that stuff to repose my 3D model. Yeah? And so this is what you're going to implement on your homework that's due next week, is exactly this. So you'll take as input, you'll take a rest pose of a triangle mesh and the bind pose of the skeleton, and you're going to come, and then you'll get a deformation of the skeleton. So your first half of the assignment is just to deform the skeleton, and the second half will be to deform the skin using a system. So at the end of the day, what do you have to do? Remember that pi is in global space of the whole 3D model. So bj inverse of pi is what? This is the position of point I in the frame of bone j, and the rest of the guy, right? So if I do this, then I end up in the frame of bone j, right? Because I apply the inverse. Now I can apply my transformation, okay? And this takes me back to global. And so that's essentially this coordinate transformation. And remember, the way that I like to think about this stuff is that essentially you should think of any matrix as taking input in the right-hand side and then spitting out output in the left-hand side. Right? So literally when you're writing your code, what I would do would be have a sheet of paper and just say like, look, remember that if I multiply by this matrix, it will take something in this guy's space and transform it into something in that guy's space. Okay? instance Bj, we'll take something, I guess, we'll go from bind pose to the local guy when I apply some inverse. And of course, you can play the inverse equivalent as well. Okay. So this is one of these things, when you try it at home, you'll get all of these inverses and the order of these kinds of products backward, I guarantee you. Okay. Right. So what is TJ, BJ inverse? It is the relative motion between the bone transformation and the current bind pose. Right? So it goes from this guy to this guy. Yeah, that's the composition for one bone. Right? And then average them all together to get what I want. Cool. All right. So then, what do we do? Well, we have these weights Wij, and I just combine these things together. And as I mentioned before, you get these usually just somebody paints them. So in your assignment, I will give you a text file with the weights Wij that usually know that somebody has done it. And this is pretty common. It's not like it's some unrealistic. Okay. So the pseudocode here is that somebody poses my mesh. I do forward kinematics, get the TJ per bone. Right, this goes from the local coordinates of the bone to world coordinates, and then now all I have to do in practice is implement this one cool formula to get all I want from SSD. Right, where if you look in the inside, this is if the whole thing moved rigidly according to that one bone, and then the average bone will go with this. Okay. By the way, do you guys remember what happens to the normals? I think this was just caught right at the end of Bo's lecture last time. Not quite. So if you multiply a matrix to something to transform, then you apply the inverse transpose of that matrix to transform. And I think Bo moved a little fast on that, so at the beginning of the next lecture, I'm going to go back and show you. But for your assignment, I thought I'd go ahead and put it here because this is pretty cool. Yeah. So again, if you move a vertex pi to pi prime using what's effectively a linear transformation, right? It's just some bunch of matrices, then you have to take the normal and apply the inverse transpose of the same matrix to get the right thing. Otherwise, like in your assignment, your shading will be off because you're doing something funny like that. And again, if this went by a little fast last time, I'll try to remind you at the beginning of next lecture. Don't let me forget. Yes?
So the assignment suggested that we compute the normals by taking the cross products of the sides. So would we not have to do that transformation, but if we could just do the transformation on the points and then take the cross product?
That's a good question.
Be the same thing?
It'll be almost identical. Yeah. Right. So you have two options, right? You could either pose the triangle mesh in the new pose and then compute the normals of the posed guy, or you could compute the normals of the basic guy and then transform the normals with him. Right? And I forget what information the assignment gives you. Like, for instance, I think it's pretty typical to actually load a triangle mesh with a normal per vertex that you wouldn't want to calculate that yourself because sometimes there are special ways to do that. If you're interested, you should take my shape analysis class. Essentially, in that case, you're really stuck using this formula, right? Because you don't have the option of like a canonical way to compute normals. But it makes sense, right? A normal is perpendicular to a surface. But remember, like the surface is a bunch of triangles. Like triangle faces have normals, but vertices don't really, right? It's a bunch of so there's like some heuristics that happen. Okay. Right, so at the end of the day, I mean, in your assignment, it's as simple as getting this formula right. So in fact, what you'll notice is that after you implement your hierarchy correctly, like after you get the skeleton bending the right way, then all you have to do is kind of insert a loop around that sums over this Wij's to get the actual scaling. And notice that the bind pose and the weights Wij are not animated. Right? The bind pose is just the way the guy modeled the mesh to begin with, and the Wij's are the influence of the bone on the skin. They have nothing to do with the motion. These are kind of common bugs. So the only things that change are these transformation matrices. And so this is a very easy thing to actually implement on your graphics card in what we call a vertex shader. So we'll come back to that later in this class. So for your purposes, you'll just do this in C++. But in reality, in your video games, because you do this to like a lot of vertices and edges and so on, you probably want to do it in your GPU instead. Okay. So there's one issue which we've already pointed out a little bit. You know, we sort of defined this transformation piecewise represented P, we applied the inverse and so on. But I can factor this expression in a different way, right? Where I just put parentheses around this thing on the left. You know? And what is this thing? This is a sum of a bunch of matrices, so it itself is a matrix. Yeah? So in other words, there's some linear map from Pi to Pi prime. Well, what's wrong here? So let's say that I had a bunch of rigidly moving pieces, right? So like my arm rotates and my upper arm rotates, but different ways. What happens if I add two rotation matrices together? Do I get a third rotation matrix? No, I don't. So as an example, a very simple rotation matrix is 1, 0, 0, 1. In other words, it doesn't rotate. What would be rotation by 180 degrees? So let's work this out, right? So let's see, start with this, right? And it maps to that. Yeah? So in other words, yeah? So is the average of two rotation matrices a rotation matrix? No, this is 0. This would take everything and collapse it to the origin. Yeah? So you have to be awfully careful the way that you and that's one of many ways to understand what goes wrong. By the way, if I get that slightly wrong, there's one of those should be a plus one. No, that was oh, it should be the other one. Regardless, things cancel in a bad way. You can get to switches. Yeah? No, that's fine. Yeah. All right. So anyway, regardless, when you average rotation matrices, you do not get a rotation matrix. That much is clear. And so the reality is that's exactly what's causing this funny artifact. So for instance, if you twist your arm, what will tend to happen is you have shrinkage. When you bend your arm, it tends to kind of have this funny fold, which you guys can probably spot. I bet you've seen it in before. And so there are a lot of different ways out of that. Typically, you have to be careful how you average rotations. That's like kind of a tricky problem in itself. What people typically do is use something called quaternion, which I think we'll talk about briefly in this class later on. It's a different way to express a rotation as a matrix. Okay. Right. So that's it for SST. It's a pretty simple technique. Not it for life. Okay. So and in reality, you know. How we figure out the weights, well, you can either paint them on the skin, or if you're given, for example, a bind pose, you can come up with some pretty reasonable algorithms that at least kind of initialize the weightings, right? So for instance, one thing you might do would be pose your mesh like 10 different ways, and then say, can you solve this inverse problem that finds where the bones and the skinny weights are because you have different poses of an object, right? So maybe you have a 3D scanner and you just watch as something moves around, and then it's reasonable to kind of guess that you might be able to find some inverse functions that guesses your motion. And so this is called automatic rigging. And actually, I think the first instance of this comes from MIT in 2007. So it's pretty recent stuff, where essentially they're given some reference animation, and they want to figure out these sort of transformations. Right? So
Pinocchio is a software system for automatic animation of 3D characters. Given a 3D character mesh and a generic skeletal motion, Pinocchio adapts the skeleton to the character and applies the motion to the shape. The result is an animated character. As we developed Pinocchio, we used about 70 different characters for testing. After Pinocchio had been completed, we tested it on 16 biped characters that we did not see or use during development. Here, all 16 of our test characters are shown. A single biped skeleton was used to animate all of them, demonstrating the generality of our approach. 3 of these characters required a single manual hint to produce a good motion. On a mid-range PC, Pinocchio typically takes under a minute to animate a character.
So related to that, you can also solve automatic skinning problems too. Let's see if this my computer is.
In this paper, we introduced an automatic algorithm to approximate a mesh animation by a linear.
So here you're given a sequence of meshes.
That is particularly effective for parameterizing motions that result from quasi-articulated motion and provides stable reconstructions with minimal parameter tuning. To skin a mesh sequence, we first estimate proxy bone transforms for the otherwise skeleton-free mesh sequence. Given the motion sequence of any triangle, we can compute its rotation sequence using the polar decomposition. cluster these rotation sequence points using mean shift clustering, and thereby estimate near-rigid mesh components. Mean shift clustering allows us to identify near-rigid structure robustly in the presence of rotation sequence outliers, and automatically determine the essential number of near-rigid components with minimal parameter tweaking. The mean-shifted triangle rotation sequences identify triangles undergoing similar near-rigid motions, from which we estimate per-frame bone transforms. For improved skinning accuracy, we use non-rigid bones obtained by fitting affine transformations to each set of core bone
So all of these
triangles.
words should sound familiar to you.
Given the bone transforms for the animation, we estimate vertex weights using automatic and robust least squares techniques. The resulting skinned animation approximates the input animation surprisingly well. The results are particularly good for articulated models. By analyzing displacement errors in the rest pose, we can generate an articulated displacement correction model that lets the skin mesh animation converge to the original animation. An important component of our approach is the efficient parameter-free estimation of non-negative vertex weights using non-negative least squares. Non-negative weights avoid very large weight bias or overfitting that can make...
They take a sequence of meshes. In this case, they all have the same triangulation, but they don't have a skeleton, right? So it's just like the pose, the paths of all the individual vertices of like this chicken over time, right? Yeah. And now, given that sequence, what they do is they cluster different pieces of the surface together that they think move nearly rigidly. And the way that they do that is they look at the motion of every triangle, and they say, well, certain triangles follow more or less the same path in rigid motion space. And they group them together, and that's what the colors you're seeing. Right? And then once they've got it into these rigid pieces, then they have a separate thing for figuring out the skinning weights that relate the motion of those bones to the motion of the actual character. They test those pretty hard test cases. Oh. Right. Not sure why you want to approximate the flying flag with bones, but apparently you can. Although you can see the artifacts of using that building. It's right, look really closely at this animation, you can see that, like right at the edges of the bones, there's some funny motion. But that aside, of course, now that they have all these skinning weights, they can have all of the horses gallop at different rates and make different poses and interact with stuff they're running into and all that kind of thing. Yeah. Yeah. When you look at graphics papers, they tend to try and stress them as much as possible. Yeah. Okay. So that concludes for today. So if you haven't downloaded your homework assignment, give it a shot, please do. And starting next lecture, we'll talk about, I think, physically based animation. So we're going to do F equals MA and couple with all this other stuff. Yes.
Stuff on the